All right. Good evening, everyone. Thank you for joining us tonight for our Caltech Astronomy Stargazing lecture, featuring an excellent guest speaker who's going to talk all about black holes and dark matter and AI and how it allows us to do things we wouldn't otherwise be able to do. So I'm Dr. Cameron Hummels. I'm a research scientist here, and I will be your MC for this evening's event. Thank you. So I'm going to lay out our schedule for tonight and have a few announcements, and then we'll get started. So the schedule for what to expect after these 2 minutes of announcements, I'll introduce our speaker. She'll talk roughly 30 minutes or so about what we have in store here with black holes and the hidden universe. And then we'll take a brief Q&A for a handful of questions for our speaker. And then it's the choose your own adventure portion of the evening where we have telescopes set up on the fields behind this building. And there's signs that you can follow to get out there. There are a number of telescopes set up with professional astronomers operating them. We should be able to see the moon, be able to see Jupiter and perhaps Venus, as well as some deeper sky objects like the Hercules Globular Cluster or the Ring Nebula or perhaps the Sgr galaxy. But stay tuned, that'll be great. Alongside, at the same time that's going on, we'll have an extended Q&A panel in this room composed of our speaker, myself, and a few other members of the department, most of which are experts on black holes. So if you have questions about black holes or, well, really anything related to astronomy or physics or the content of the presentation, feel free to stick around and ask our panel, and we'll do our best to respond to whatever questions you may have about these sorts of things. And all of these events, both the telescopes as well as this, will go until 9:45 or so, 10 or so, and then it's the end of the night. We do these once a month on a Friday night. Our next one of these will be June 26th, Friday, June 26th, the end of the month. I don't yet have a speaker, but I've asked a few people, and I'll have it announced and advertised in the next week. So stay tuned on however you found out about this event. It'll be announced through the Caltech calendar and our website and social media and all the places. In addition, I should mention we now have a camera person recording these. So if you miss or there's some favorite part of the talk that you want to re-experience, you can go on YouTube and check it out, as well as hi live stream audience that's watching this now. Some special events that are happening in 2 weeks' time here. The American Astronomical Society, this is kind of the professional society for all the astronomers in the US, is coming to Pasadena the week of June 15th, and they'll be at the Pasadena Convention Center. And so as part of that, we're going to have a number of different public events that are going on that week. So Sunday, June 14th, 2 weeks from this coming Sunday, there will be a City of Astronomy Astro Festival taking place at the Pasadena Convention Center from 1 to 5 p.m. on Sunday. And it'll feature science demonstrations and booths and 30-minute public level science presentations from astronomers all around Pasadena, from Caltech, from the NASA Jet Propulsion Laboratory, from Carnegie Observatories, USC, the Planetary Society, Griffith Observatory, all the main players in town. And it's all free, and you don't have to get tickets or anything, just show up, and we'll have telescopes, and we'll have the cool VR headsets that hopefully some of you got to see through in the lobby, looking at a rendition of what a accretion disk around a black hole might look like. So that'll be Sunday, June 14th. And then that week, Monday, Tuesday, Wednesday of that week, we'll have 3 separate Astronomy on Tap events. Astronomy on Tap is a kind of a sister series to these events taking place at a bar in Old Town Pasadena, the Doghouse Beer Garden. Even though it's a bar, it's open to all ages and it's all outdoors. It's usually pretty fun. We get a few hundred people who show up. Those events are on, as I said, Monday and Tuesday and Wednesday. They consist of 2 15 to 20-minute public level like this, but shorter and in a less formal setting than a university campus, presentations, as well as astronomy-themed pub trivia. There will be some live music and telescopes. So I encourage you to show up to that. Again, like these events, it's free and should be a lot of fun. And we're getting our speakers from the visiting astronomers who are coming from all around the country to this event. So it should be really fun. I think those are all my announcements. So So that brings me to our speaker tonight. Our speaker grew up in Indiana. She did her undergraduate studies at University of Michigan studying electrical engineering. And then she went to MIT, where she pursued a master's and PhD in electrical engineering as well as computer science. And it was at that point that she became involved in the Event Horizon Telescope, which is this multinational consortium of telescopes, of radio telescopes that are able to, well, they were able to take the first image of a black hole that had ever been taken, albeit in the radio part of the spectrum. And I'm sure we're going to hear about that tonight. And she, when she finished her PhD at MIT, she began a postdoctoral fellowship at Harvard for 1.5 years before coming here as a professor, which she arrived in 2019, and she's been here ever since. She has earned a number of accolades. She's a Sloan Fellow, a Rosenberg Scholar. She's a TED speaker, TED Talk speaker, and she was BBC's 100 Women of the Year 2019. Yeah. And her research is all about computational imaging and computer vision and artificial intelligence to make some really breathtaking and groundbreaking images of things that we aren't otherwise able to see in the physical world. So please welcome our speaker, Professor Katie Bouman. I can't hear the audio.
Oh, is it? Oh, that's good. Can you hear now? Okay. But this motion that we see from the stars is evidence of a black hole, but it's evidence from motion, not from sight. And there's always been this push to go one step further in order to not just detect something that's there, but to actually see it. And that's because images make the abstract feel tangible. You know, the first image of DNA, the first image of an X-ray, the first image of our Earth from space. All of these things made these abstract phenomena feel really tangible and helped us understand what we were studying. So even if we believe there is a black hole there, there's a natural question of what does it look like? But black holes are very strange. They trap light. So how can you even begin to see something that, you know, is fundamentally invisible? So black holes are one of the most extreme predictions from Einstein's theory of general relativity. And for many years, that's just how we understood them, as equations. And as those equations turned into rough sketches, physicists began asking a question of, if black holes are real, what kind of imprint would they leave on the light around them? And actually, in the late 1970s, Jean-Pierre Luminet actually went about trying to answer this question and used an IBM mainframe computer with punch cards to actually calculate what the path of light would be around a black hole if general relativity was correct. And the output from this IBM mainframe computer, he actually hand drew the result with liquid India ink. And this is the negative of that picture that he drew by hand. So this isn't an observation. There's no data here, but it was for the first time a prediction where we could actually see, well, what is it that we would expect the environment around a black hole to look like? And even as those simulations improved, the same core prediction remained, that if we were to see a black hole, we would expect to see this ring of light. Why? Well, light propagating near a black hole doesn't follow straight lines. It's actually curved because the black hole is curving space-time. And so the space around a black hole is actually lit up by this hot gas that's heated to hundreds of billions of degrees, and it has photons flying around everywhere. Some of those photons fall into the black hole, but other ones just graze it and are bent around, such that the net effect is that the black hole casts what we call a shadow on this backdrop of hot material that's almost perfectly circular. So we don't actually see the black hole itself, but we would expect to see the imprint of a black hole. And if Einstein was right, then we would expect if that compact mass is a black hole, we would see a shadow of a very particular size and shape. And that would help confirm if this is actually a black hole. And so for decades, physicists believed that going after and seeing that ring of light would help us confirm the existence of black holes. But actually getting the required observations to see that seemed nearly impossible. And then 7 years ago, we actually were able to do it. So we took the very first image of a black hole. This is the image of a black hole in a galaxy called M87. It's 55 million light years away from us, and it was the very first black hole that the collaboration, the Event Horizon Telescope collaboration was actually able to see, or that humanity was actually able to see. And then 3 years later, we did it again, this time imaging the Sagittarius A star black hole at the center of our own Milky Way galaxy. We like to call it Sag A star for short. And these images made the front pages of newspapers around the world, which was really exciting to us when that happened. But there was one thing that always really bugged me when this came out, and that's that they always just showed one image. And that image is powerful, but it doesn't tell the full story. And that's because there never was one image, just one image. In fact, there was hundreds of thousands of different images, huge collections of images that actually were computed using different algorithms, different assumptions, and they result in different images with slightly different features in them. And so all of these images you're seeing are actually matching the data that we have. They fit that data. So then a natural question you might have is, well, which one is the right image? And well, the answer is like based upon the data alone, we don't know. But what I kind of want to get across today is maybe we need to let go of this feeling of needing to pin down an image perfectly. Maybe we need to embrace the idea of uncertainty and the fact that we not necessarily can get all information, because once we let go of needing to recover the truth perfectly, then we can open ourselves to being able to recover things that would be completely impossible otherwise. And so that's what I want to show you today. By using limited information along with a range of different types of assumptions, including those enabled by machine learning, that we can actually use that to try to piece together an understanding of what is going on in this unseen environment. And so before getting into that, though, I just want to again get into why is taking an image of a black hole so hard? Okay, so these black holes are really far away from us. And so even though the physical size of their event horizon is actually really quite huge, they're so far away that on the sky, they appear incredibly small. It's about the same size as if you say you tried to take an image of a single grain of sand. But if that grain of sand is in New York and we're trying to view it all the way from where we are in Pasadena. And so taking a picture of something that's that tiny, actually you can compute just through simple equations that you need to build a telescope the size of the entire Earth in order to do that. And of course, we can't build a telescope the entire size of the entire Earth, but for a minute, let's just pretend that we could. Okay, so for radio wavelengths of light, a radio dish like this just acts like a giant mirror. So light from the telescope is going to travel to Earth, it's going to reflect off the mirror, and then we're going to collect that light. And the key to being able to get a really sharp image to see that fine detail is we need to collect light over a very large area, this very large aperture, as we call it. And so the key is collecting all that information. Okay, so we can't construct one Earth-sized mirror, but what if instead we laid mirrors all across the Earth, essentially turning the Earth into a giant spinning disco ball? Well, then we can collect light at each one of these tiny little mirrors, freeze that light, bring it to a common location, and use our computers to act like the lens to make that final picture. And it would be just as good as if we had a one Earth-sized mirror. Okay, but then what happens if we remove most of the mirrors so only a few remain? Well, then can we still make a picture in that case? Well, that's exactly what the Event Horizon Telescope's collaboration set out to do. So we brought together hundreds of different scientists and engineers from all around the world who worked on trying to make a computational telescope the size of the Earth capable of resolving structure on the scale of a black hole's event horizon for the first time. And how this worldwide network works is that we have telescopes located around the world, and they're actually linked through the precise timing of atomic clocks. So we essentially freeze light at each of these locations, and then we actually fly them with airplanes, that data, to a common location, and then use our computers to combine it and to make an image. And so this network of telescopes doesn't act like your typical telescope. Instead, in this one, we use information from pairs of telescopes to form the image. So telescopes that are far apart detect the smallest, sharpest features of the image, where the orientation between those telescopes tells us about details in different directions. And so if you have all the orientations, you're going to get all the detail information at a certain scale. And then if you have telescopes at different separations, that gives you information about different scales of the image. So in order to see the full image, we would actually need telescopes at all different orientations and all different separations. And so making a perfect image would require, again, that we have telescopes all across the globe to get all those possible separations and orientations. But in the Event Horizon Telescope, we only had a few telescopes. So that means we're only getting a small number of points there, so not a small number of the possible pairings. But luckily, as the Earth rotates, the baselines, the separation and orientation between the telescopes actually changes. And this amounts to carving out these different elliptical paths in that space of orientations and separations. And so we don't get all the information we need to make a picture. There's still a lot of missing data there. So how do we take that and then make a picture from those measurements? Well, at this point, we can kind of abstract away the astrophysics of the problem and just think about it as a purely mathematical inverse problem. So we have these measurements, they're incomplete, and our goal is to find the image that relates to those, that cause those kind of measurements. And again, if we were given measurements across the whole globe, this would be pretty trivial to compute. But because we have only a little bit of data, since we're missing data, that means there's actually an infinite number of possible images that are perfectly consistent with the data we measure. And the fact that we have a different atmosphere above each of our telescopes, like we have a different atmosphere above Hawaii, then Spain, then Chile, that means that it makes the problem even more challenging. And there's a larger space of possible images that are consistent with the measurements. So how do we deal with that? Well, of the images that are consistent with our measurements, there are some images that we consider to have properties that we like more than others. For instance, we expect the image to be smooth, or the light to be compact, or light to be positive. And so we can try to impose some of these simple statistics about what we think images should look like, and turn the problem into not just finding one that is consistent with the data, but also finding one that looks like some mathematical representation of what we think a plausible image is. And so by injecting preferences such as that into the algorithm, we can whittle down from the infinite possibilities to potentially one image that fits our data and looks plausible. So I like to say watching the black hole with the Event Horizon Telescope is a little bit like listening to a song being played on a piano that has a lot of broken keys. So even though you don't know what is being played, how the broken keys are being played, you can still oftentimes figure out the song. So I'm going to play a song on a broken piano, and I want you to raise your hand once you think you can recognize the song. So I'll play it now. So I saw a few early hands, but I think that at some point, most people started to recognize it as happy birthday, right? And that doesn't, there were a lot of missing notes, so who knows, you could have been hitting those notes in any kind of random way, but our brains are able to kind of fill in the gaps in a reasonable way. And that's kind of what we have to do with making the image from this very limited data. So you might still be pretty suspicious. You're like, well, if we're making an image that way, is it really using the data, or is it just you making up some sort of image based upon your assumptions? But actually, the idea that an image is formed based on assumptions is actually something we rely on pretty much every image we look at. For instance, if you go in and get a medical scan done, no one's like chopping open your head and snapping a picture, right? Instead, you're using something like an MRI scanner, which makes measurements that are connected to that image through some physical equations. And converting those measurements into a picture actually requires assumptions. And yet we still trust medical images. We trust it enough to make medical diagnoses off of them. And even potentially something as simple as a photo from your digital camera, this is also happening. When you snap a photo, every pixel that your camera captures is only capturing the red, green, or blue information. The other pixels, so if it captures red, the blue, and green, are just being computed from the nearby pixels. And so actually, when you take a digital photo, 2/3 of the information is actually completely made up. And yet we're totally comfortable with that. So computation and assumptions aren't unusual. They're actually fundamental to basically every image that we look at. But images lie on a spectrum. On one side, like our everyday photographs, we have so much data that we're working with that even though our images rely on assumptions, the semantic meaning of what we get out, kind of the structure of the objects that we're imaging, don't change drastically based upon the assumptions that we use. But on the other side of the spectrum are things in the area of cutting edge scientific imaging. And in this case, our data is much more limited. And so they rely much more on those assumptions, and those assumptions can really strongly shape the images we get out in the end. So how do we deal with that? Well, instead of just having one set of assumptions that we impose, instead what we can do is we can impose a whole collection of different types of assumptions and see how that affects the images we get out. So for instance, when we first published the results with the Event Horizon Telescope, what we did is we didn't have just one image. We actually computed a whole collection of different types of images using different methods that were computed with different assumptions. And we could change out those assumptions or increase or decrease the strength of them. And importantly, those assumptions had nothing to do with the physics of black holes. Really simple things just about like the smoothness of an image, light is positive, things like this. And we searched over about 175,000 different settings and saw how those settings affected the images we got out. And that's what resulted in this collection of all these different types of images that we saw. Again, each of these images is actually fitting the data, but as you notice, they're all slightly different from one another. So in order to emphasize the common features appearing in most of them, we averaged them together. And that's the image that made the newspapers. So even though we don't know exactly which of those images is correct, what we know is that they all are kind of pointing us in that direction that it looks like that ring is probably real. And in fact, the ring that we recovered has a diameter that fit perfectly with prior observations in theory. So two very different looks at this compact object at the center of our galaxy, one that relied on the motion of stars, like I showed at the beginning. And this one, what the Event Horizon Telescope did, looking at the bending and capture of light, these two very different views, both aligned with Einstein's theory of general relativity for a black hole of 4 million solar masses, which was a really exciting validation of general relativity on a new scale. And it's unlikely that it was just some sort of coincidence because we saw the same thing a few years earlier when we imaged a very different black hole, the M87 black hole, that is a very different mass. So this was really exciting to us. I mean, it's one thing to make a prediction, but to actually see it come true was pretty exciting. So after literally years of working on this data, we were ready to publish it. I was lucky to be selected as one of the people who would present the work in a press conference in DC. And we prepped all for the day, trying to figure out all the tough scientific questions people would ask us, so we were ready and prepared. And then on the day, this was one of the first questions we were asked.
Next question is Roberto with G1 TV Global Brazil. Why was the first ever black hole image blurry, and should we expect to see more detailed images?
So of course, like one of the first questions is like, why is your result so bad? So, I had to give a little bit of a snarky response. This image is actually one of the sharpest images you've ever seen. You know, it looks blurry on the screen because we only are seeing a few pixels, but actually it's the sharpest, one of the sharpest images ever made. And although what I'm saying is actually true, it is actually one of the sharpest images. I'm being unfair, right? It's probably when I showed you the image is the first thing you thought. It's so blurry. I know when I showed my family after years of working on it, they're like, oh, why, you know, like not so impressed. And of course the internet had a very similar reaction. so again, why can't we get higher resolution? So remember, the detail that we see in an image is related to that maximum separation between the telescopes. But we're already at the maximum separation that we can get by having the telescopes here on the Earth. And so in order to see more detail, we'd actually have to go to space, which is something people are thinking about, but it's not going to be happening anytime soon. And so we're wondering, can we do more with the data we have already? Well, so far, the imaging results I've been showing you used very weak assumptions, things like I talked about, like the smoothness or compactness. And that's important because when we're first testing the idea of if this is a black hole, we don't want to put in our assumptions of what a black hole should look like. We want to be agnostic to that. But once we start building in confidence, hey, this is looking more and more like our expected physics, then you might ask a slightly different question. You might ask, can we use the physics that we know to help us even pull out more from this data? And that's what I want to focus on for the rest of the talk, how we can start to introduce stronger and more informative assumptions to get more out of our limited data. So I'm going to dive into the first direction on using learned assumptions. Okay, let's consider different ways that we could try to take that data and make an image. On the left-hand side, we have really weak assumptions. That's like what I showed you before. And the disadvantage of this is, the advantage is that you're not biasing yourself too much in one solution, but the disadvantage is you're not going to get very rich solutions out. And on the right-hand side, you're going to have very strong assumptions like model fitting to a model of black holes. And the disadvantage of this is we really limit our ability, our potential for discovery, and also you risk overfitting to an incorrect model. So we really want to target the middle where between these two extremes. And one way to do that is to try to let data tell us what kind of images we might want to help, we might want to like encourage in our results. And so, for instance, instead of hand designing a set of assumptions, a mathematical equation that gives us some assumptions, instead what we're going to do is use an AI model to take a collection of images that we learn, and for the AI model to kind of figure out what makes this kind of image look like this kind of image. And once we've trained that on data, then we can actually sample from that model to get out computer AI generated images that actually mimic these kind of real simulations, but are completely just samples from our AI model. And the advantage, and importantly, even though this can represent really complex structure like the physics we see in these simulations, it's still a mathematical object. And so it can be combined with the physics of the measurements in an inference engine to solve for an image that both respects the measurements and also looks like something that we would expect to see. And so here you can see what happens when we actually use one of these data-driven priors, what we call it, these data-driven assumptions based on simulations to try to take the data and interpret it in a way that looks like, for instance, our current understanding of black hole simulations. But one power of this approach is that we can target different assumptions by simply changing that data set. We don't have to like really think very hard about how to write down a new mathematical expression. We can just simply change out our training data and train a new model. And then use, and then those images, those assumptions we compare with the exact same physics in order to see how the image would change based upon these different assumptions. And one of my favorite examples is even when we tried reconstructing the black hole image with using a data set of celebrity faces here on the right. And even though the result is somewhat unsettling, like we have the Phantom of the Opera in the center of the galaxy, what I love this example so much because it tries its hardest to still make that ring structure out of the eye socket of the person. And so that's kind of the point I'm trying to get across, that if you look at any one image in isolation, it's really hard to know what to trust. But when you look across them, that's when something very clear emerges. Which image features are robust and which ones are not. And so this is what my former student Berthy Feng did. And she found for the M87 black hole data that two features consistently survived: the diameter of the ring and also that brightness asymmetry. So those weren't being hallucinated by our assumptions. The data was telling us that that's correct. And those features are scientifically meaningful. The brightness asymmetry tells us about the motion of the gas, and the diameter of the ring tells us if this is a black hole, how much does it weigh? So we don't need to know about what the exactly true image of the black hole looks like to still get out a lot of scientific information from it. Okay, great. So now that we know we don't need to just rely on simple priors, we can use these different learned assumptions to try to really quickly see how our image changes based upon different kinds of image assumptions. And that allows us to do a lot. But what if we even push this even further? For instance, what if we said we don't just know what an image looks like in a statistical sense, but for instance, I trust that general relativity is correct. Well, what can we do in that case? Well, it turns out we can do a lot, and we can even pop out of the 2D image plane and start to see what might be moving on around this black hole in 3 dimensions over time. How can we do that? Well, to understand, let's first consider how traditional tomography kind of works. So if you go in, for instance, get a CT scan done, what is happening is you're actually collecting information, projected information about your body in all different directions, and you can use that information to kind of to constrain a reconstruction problem that allows you to see what the inside of your body looks like. So we want to do a similar thing. We want to recover 3D, but we have 2 big challenges that separates it from traditional kind of tomography, like in medical imaging. One is that our rays are curved. They can't even go in complete circles around the black hole. But the more challenging issue is that we're only ever seeing the black hole from one direction. We don't get to see all the different sides of the black hole. We only see it from Earth or very close to Earth. And so how do we possibly get around this? Well, by injecting some of the expected physics back in. Okay, as an example, let's say you go into the doctor and you're like, have some problem, and the doctor's like, oh, we need a CT scan done stat, right? So they bring you to the CT scan, you get you in and press the button and it doesn't work. But the doctor is like, oh, I really need this. So she's like, oh, can you rotate your body in the scanner? And if the doctor knew precisely how you were rotating your body, then theoretically, she could reconstruct a picture just the same as a functioning scanner. So we're going to try to use a lot of the same kind of information by knowing how gas is moving around the black hole and how light is bending, as defined by things like general relativity. We can try to back out what the 3D structure is. And in particular, this is what Avi and Levis and our collaborators did. We built this whole end-to-end deep learning model that tried to, that used constraints from the physics that we believed were likely to be true to constrain a problem and allow us to reconstruct what the emission at some initial time t was, at some initial time, that allowed us to see what was maybe happening in 3 dimensions over time around our black hole. And using this approach, we were able to actually somewhat remarkably reconstruct what was happening around the black hole in the center of our own Milky Way galaxy on April 11th of 2017. So on that day, there was this big flare, a big bright thing that happened, and we thought there might be something there, but we didn't know what it was. And when we did the reconstruction, we saw it looked like at some initial time, there was these bright spots that showed up, what we call hot spots. And over time, and these hotspots showed up about 75 million kilometers from the event horizon. And over time, if you project forward in time, they started shearing out. So you could see them shearing out around the black hole over a period of about 100 minutes. So overall, I want to highlight that this solution is super uncertain, right? It relies on these strong physical constraints in order to solve this problem. And those physical constraints are somewhat unknown, right? That's what somewhat of what we're kind of studying as well. But I still find it really exciting that if we were to say, oh, we believe them, or we believe them up to some perturbation limit, we can start to not even just see our black hole in 2D, but start to recover information in 3 dimensions. And so that's what I hope I'm getting across today, is what's really powerful is not any single reconstruction, but it's about seeing the full range of possibilities, the whole family of black hole images, and seeing how different assumptions change the result we get. And through all these different types of ways of viewing the same data, we can try to piece together an understanding of what's going on, what do we think is robust and what is not as robust, but what do we believe under certain kind of different conditions. And I want to highlight that this is really just the beginning. We have so many points on the spectrum we have yet to explore. And I think it's really about seeing this data in all different ways that allows us to build an understanding of our unseen environment. But this idea is so much more general than black holes, because across many problems in science, even if they look really different, you share a lot of the same fundamental problems. Trying to recover information, images in our case, from very limited data. And so I want to highlight one other problem very quickly, where methods that we developed largely for black hole imaging have actually allowed us to accelerate discovery in other fields. Okay, so when you look up at the night sky, you'll see light from gas, nebula, stars, but in reality, that's actually less than 1/4 of all the matter in the universe. The majority is actually dark matter. It emits no light, and so we can't see it directly. So if we can't see the dark matter, how do we actually go about trying to recover what's there? Well, the only way is to infer its presence through its effects of gravity. How? Well, as light from distant galaxies makes its way towards our telescope, it's actually going to pass through massive lumps of matter. And the gravity from the matter, the large majority of it being dark matter, is going to bend the light ever so slightly, a process called gravitational lensing, which is the same as what we had during the black hole with the light bending around the black hole, but it's just much, 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 much weaker. And this results in a change between the galaxy's intrinsic shape and the one that we actually observe at the telescope. And so that distortion that we see actually depends on the matter, the density of the matter between the galaxy and our telescope. And thus measuring these shape changes actually is a probe into what is the dark matter distribution in our universe. But this is an incredibly challenging inverse problem. Actually, the distortion that I'm showing here is hugely exaggerated to what it actually is. In reality, it's extremely small. The signal that we care about is barely visible. And on top of that, we actually don't know the intrinsic shape of the galaxies themselves. We don't know what the original shape is. So we don't know if the shape that we see is because that was the original shape of the galaxy or because it was distorted in that way. And so this uncertainty from not showing the shape is much larger and causes the problem to be super noisy, and we basically get no information from any single galaxy. But if we look across many, many galaxies, something kind of remarkable happens. And that's that statistically the shape of galaxies in a common region are all going to be slightly shifted in the exact same way. And so we can use that information, we can combine the information across hundreds of thousands of galaxies in order to exploit those spatial correlations and figure out what kind of density of matter is in that particular region. And we can also use the distance that we know to each galaxy to recover not just how much density is in a region in the sky, 2D region, but we can try to pinpoint it in 3D as well. As you might expect, though, the physics here, it still isn't strong enough to fully constrain the problem. So again, we have to merge it with assumptions. And this is what my student, Brandon Zhao did, who will be here for also the Q&A session. And so he did this really awesome thing where he took these simulations that were actually computed by other people, these cosmological simulations, and again, trained a prior on them, trained in these assumptions on them, and merged it with the physics of the gravitational lensing signal from the shape changes of the galaxies in order to recover what the 3D structure of dark matter is in a particular region. And again, this is actually using the same rough inference engine that we actually developed largely for black hole imaging. So we're able to transfer those tools to a totally different problem. Before showing results in 3D, I just want to show what reconstructions of recovered dark matter fields look like for simulated data in 2D. So here is, for example, our simulated data of dark matter. And in the middle is the reconstruction that Brandon was able to do. And as I hope you can see, you can get a lot more of the detailed structure than you can using traditional kind of methods. But even more importantly than that, to me, is that we get a sense of the uncertainty of the problem, because there is a lot of uncertainty, just as there was with black hole imaging. So we're not restricted to just one solution, but by seeing a whole distribution of possible images, we get a sense of what that uncertainty is. But now on to 3D. So here is kind of an example, again, for a simulated data set, that the fact that we can reconstruct not just the 2D distribution, but actually the 3D distribution of dark matter. And again, not just throw it all into one image to get a blurry reconstruction, but see many possible realizations of what the dark matter might look like in a particular region of our sky. And so the last few months, we've actually been applying this to the James Webb Cosmos field in collaboration with people from JPL. And although we're still in the process of doing that, we're getting some really exciting preliminary results. So I hope I'll be able to share those with you guys soon. So I'm really excited for where this is heading. But stepping back again, I hope what this shows is, what many of the most important problems in science today are not directly imaging things, but they're doing indirect imaging. And we have to use computation along with assumptions in order to recover some meaningful scientific information from them. And for the longest time, we've just tried to collapse that down to one image. But I think what's important is that we embrace the uncertainty of these problems. And in doing so, we are able to better understand what we trust and what we don't trust. And what's really exciting is now we're beginning to have the tools to do this in a much more systematic way. So for instance, the tools that we developed largely in some cases for black hole imaging, we found are applicable not just to dark matter imaging, but to a wide variety of different types of problems in scientific imaging. And so we're trying to come up with ways that we can develop these frameworks so we don't just have bespoke tools for every different type of method, but we can have shared tools that we can translate across problems. And through that, I hope, accelerate scientific discovery and begin to understand the hidden universe through its many images. So with that, I just want to thank lots of people, the entire amazing Event Horizon Telescope collaboration, which I had such a privilege being able to work with. But in particular, I want to highlight Berthy Fang, Aviad Levis, and Brandon Zhao for leading the work that I talked about today. So, happy for questions.
We can take a few questions. I'll pass the mic around first.
Thank you very much. Thank you. That was a wonderful talk. I really enjoyed it. What is the inferred velocity of the shearing that's occurring? Is it around M87 or is it at Sagittarius A?
That's Sagittarius A star. I don't know offhand.
It might be relativistic.
So, okay, this is far enough out that, okay, yeah. So one thing is this is far enough away from the event horizon that we can actually assume at that point Keplerian orbits. When you get in closer to the black hole, let me get to the picture. So it's just, sorry, I have to find it. Yeah, when you get in closer, then you're going to start to have other gravitational effects of infall and stuff like that. So actually, we have some follow-on work that we've been working on that we're presenting soon, but still only on simulated data, where we actually not just constrain the velocity, but we solve for the velocity simultaneously. And by doing that, we're hoping to be able to push our ability to reconstruct things even closer to the event horizon. But at this point, for things this far away, we're assuming Keplerian and sub-Keplerian orbit. So in the paper, we show, if it's, for instance, 70% of a Keplerian orbit, how does it change the reconstruction? And we found between Keplerian orbits and about 70% of a Keplerian orbit, we get the same solution. And then if we go even more sub-Keplerian than that, then things start breaking down.
So you don't have an order of magnitude estimate yet on the
I don't remember. Sorry, I don't.
Okay, that's okay. I'll get your email and you can send it to me.
Additional questions? You have a question? We'll do it during the panel. Okay.
Thank you.
First, thank you for the great subjects. I have a question about the blurriness of the picture that you mentioned.
The what of the
The
picture?
blurriness of the image.
Oh, blurriness, yeah, yeah.
Yeah. What makes an image not blurry is hard edges, I believe. Is there theoretically hard edges in a black hole that if we can take a picture, a very high quality picture, do we
Yeah.
expect to see any hard edges and not a blurry image?
Yeah, actually, I don't know if I have good
Thank you.
simulations actually, but actually the point, there's a point where photons are orbiting nearly indefinitely. They're on unstable orbits, so they kind of fly off towards us, but there's this point that they kind of where photons orbit around the black hole, and this is called the photon ring. And this is a sharper ring around the black hole, and that's actually the information, the most informative part. If we're able to actually see that ring very precisely, we're able to test GR, for instance, more accurately than we can now with our kind of blurry image. So and that's a very sharp ring. So one, for instance, and also you're expected not to see one ring, but there's actually nested rings that get tighter and tighter, closer together. So actually being able to see that ring and and how those rings are nested could actually be a really important probe into studying general relativity. So this is one kind of target for doing a space mission, like putting a telescope in space, a space telescope with a baseline on Earth and very far away would be able to hopefully be very sensitive to that really high frequency. So you wouldn't be able to necessarily be sensitive to that really fine ring structure. So you might not necessarily be able to make a picture, but if you believe that that ring exists, then it would be, you could very precisely measure, for instance, the diameter or shape of that ring. So that's one thing that's really important.
Okay, another question here.
So you mentioned that the diameter of the Earth is a constraining factor on the aperture of our synthetic aperture telescope. But the Earth is also orbiting around the sun. And so could we use measurements taken at like 3 months apart or 6 months apart to create a 2 astronomical unit wide aperture?
Yeah, really good question. I wish we could, but unfortunately we can't. Remember, the data that we collect has to be the information that we use to make the spatial frequencies of the image actually has to be taken simultaneously. And so this is why we actually have atomic clocks at each of the locations so that we can precisely time them. And then we actually have to align them to sub-picosecond precision. And that's what we allow us to get the data. So you can't take data that was taken at one time with half a year later or something like that, unfortunately. But yeah, good. Yeah, well, we are working on, actually, I didn't get to it in the talk because of limited time, but we're getting to actually making videos of the black hole. So stay tuned for that in the future.
Cool.
Yeah.
Cool. We'll just have a couple more questions.
Hey, every year, people, all around the world, researchers do black hole imaging, and angular resolution of it just keep increasing with the effort and innovations. But how do you achieve that angular resolution with thick amounts of clouds surrounding the entire galaxy, especially the black hole? Like, how are you achieving that amount of angular resolution? Like, I've seen a simulation of where there are like 10 to 20 stars whipping around a black hole image that was our simulation made by European Space Agency, maybe?
Oh, it was actually, those are observations, but yeah.
Oh, yeah. So how did you guys achieve it with so many noise and thick cloud, dust, and yeah.
So, well, there's lots of parts to that question. So really the thing that we're trying to image is teeny, teeny, tiny. So you can think of it like there's not really other stars like going in front of it in our field of view. We have a direct view kind of that. There is other stuff, for instance, the black hole in the center of our Milky Way. There's something called interstellar medium between us and the black hole, and it actually causes it to, it's kind of like looking at the black hole through a frosted window or like, you know, a shower screen or something like that. And so it does kind of affect the image, but it's not like you have a cloud kind of going over it or anything like that. We do have to deal with the fact that all our telescopes around the globe have different atmospheres above them and different water vapor levels, and that actually makes our data super noisy, but it's something that we have to deal with. Even in the tiniest amount of noise that there is, you're always going to have that kind of noise. Yeah.
Do radio telescopes form the infrared probes, like infrared actually gets through the dust and clouds, and it actually gives you a understanding of data?
Yeah, it's a really good question. So actually, we kind of got really lucky with these two black holes. So these black holes, the Sagittarius A star and M87, are the two biggest ones that we know of on the sky. And think at shorter wavelengths like infrared, we're affected by things like the dust, and we actually can't pierce through to see that event horizon. And longer wavelengths, we also are affected by, well, one is that you actually would need even a bigger telescope in order to get the same resolution, but also the emission is coming from outside, farther out, like the gas that's kind of cloaking the black hole. And so again, we don't get that ring of light. So that ring of light kind of appears very close to about a 1 millimeter wavelength or 230 gigahertz. You can move a little bit here or there, but not like all the way to infrared and not all the way to longer radio wavelengths. So we have a very precise kind of set of wavelengths that we can work with. And for those wavelengths, it just so happens we kind of got lucky that we needed a telescope the size of the Earth to see them. So, you know, nature was working in our favor in that way. Yeah.
Okay, in interest of time, let's thank our speaker. Okay, so now is the choose your own adventure portion of the evening. We've got telescopes set up behind me. If you want to go look through those, you can go out the front doors and follow the signs to the athletic fields back here. And in about 5 minutes, we'll start our Q&A panel consisting of Professor Bouman, myself, and a few other members of the department to answer questions related to the talk or about black holes or about whatever you read about in astronomy and physics and in the news or whatever. But feel free to jump between the telescopes as well as in here over the next hour or so. We'll keep them going. So thank you guys for coming, and hopefully we'll see you guys next time. Okay. Thanks everybody for sticking around. So now we'll begin with our Q&A panel. But to start out, each of us will go through and just give a short introduction of who we are, what our science is, and we'll take questions on whatever topic you have. But if you know a little bit what our specialty is, we may be able to answer more precisely the things that are related to our research. So I'm Cameron Hummels. I'm a research scientist here and director of astrophysics outreach. My research is primarily on cosmological simulations like Katie talked about, but more looking at how galaxies evolve within that context, and then trying to make, because galaxies take a very, very long time scale to change. Our Milky Way galaxy takes, has lived its life over billions of years. And I don't know about you, but I haven't lived my life over billions of years, at least not yet. And so it's hard for us to see galaxies changing in real time because they have such long timescales. But we use computer simulations to model that, where we can artificially speed up time in the simulation and see how things change over very long timescales. And we can compare those simulations to actual observations of galaxies to try and back out what some of the relevant physics that's going on in galaxies and how they live their lives.
Hi, I'm Katie. I think you guys all probably know what I work on now. I'm more on the computational imaging side. So I can answer questions about the Event Horizon Telescope, but if you have specific black hole questions, ask them to the other people.
Hey guys, I'm Brandon. I am a grad student in Katie's group, and she, I think, mentioned me a couple times in her talk. Mostly I work on dark matter stuff, like was mentioned, and I also have dabbled a little bit in the black hole videos, but happy to answer any questions.
Hi everyone, my name is Cheyenne Shariat. I'm a PhD student here, and I work on stars in binary and triple star systems. So the three-body problem, if you've heard about that, that's what we're trying to understand using detailed three-body simulations on our computers, and also by going and looking at triple star systems and how they evolve. And so if you evolve stars, sometimes you get black holes much smaller than the ones that Katie talked about, more like the mass of our sun, but these are incredibly common, and they're dormant, and they're residing all over our Milky Way, hundreds of millions of them. And so I'm trying to disentangle that and understand that in my research through observations, looking at them, and simulations modeling them.
And hi, I'm Kristen. I'm a postdoc here. And black holes come into my research in a very different way. So when two black holes or other compact objects get really close to each other and collide, this collision is so violent that it actually creates ripples in spacetime itself. We call those ripples gravitational waves, and that's what I study. So I use gravitational waves to try and learn more about fundamental physics, like how does the theory of gravity work, and to learn more about the universe, like how fast is the universe expanding.
Okay, so now we open it up to all of you guys. If you have questions for our panel, we'll also take questions from our online audience as well. You always have good questions. What do you have for us, sir?
What is the evidence of each three of the Big Crunch, the Big Rip, and the Big Freeze?
Boy, it jumps right into it. What is the evidence that we have for the Big Crunch, the Big Rip, and the Big Freeze? I mean, we don't yet have evidence. Okay. So let's first introduce those. Does somebody else want to take this, or do I have to cover this? Okay. So let's introduce what our young gentleman has questions about. So he asked about the Big Rip, the Big Crunch, and the Big Freeze. These are three different possible end states of our universe, basically what our universe will eventually evolve to. Everyone's familiar with the idea of the Big Bang. It's the most popular term for the most popular version of the formation of our universe. It's formally called lambda CDM, lambda cold dark matter model of the universe. But the idea is that about 14 billion years ago, there was a large expansion of space-time that's continued outward, in some ways accelerating. That was learned about 20 years ago, 25 years ago through some observations of distant supernovae, but this is expanding. And the question is, what is the end point of this? So if there's enough gravitational mass within our universe, then gravity wins and it reaches a point of furthest extent, and then it collapses down upon itself. And that's what's termed the big crunch, because it's kind of the opposite of the Big Bang, everything collapsing down onto a small point in space or in space-time. The big rip is kind of the opposite, where it's expanding, and as I mentioned, it's accelerating in its expansion, and the big rip is the case where it continues to expand and accelerate indefinitely, and eventually the space-time separating everything, even the molecules in your body, starts to expand and everything rips apart. Also, these are kind of unpleasant things to think about in the distant future, but don't worry, this is the distant future, so it's not going to really affect you. And then there's kind of the in-between, the big freeze, where things are expanding outward, but eventually they at time equals infinity, that expansion stops. And this is called the big freeze. So these are kind of the three possible phenomenological ideas for the end state of the universe. And the question was, now that we've done that mouthful, the question was, what are the pieces of evidence that suggest one or the other? The prime thing to consider is what the geometry of the universe is, the flatness parameter, which right now it appears to be a flatness of 1. So it appears that probably it's going to be the big freeze. The other thing that is relevant here is, what is the mass density of the universe? Do you have enough mass to cause a collapse of everything upon itself and turn into the big crunch? And it does not appear that we have a mass density greater than the critical density that you need to cause this big crunch. So we think that it won't be right now. Current suggestions based on observations that we have suggest that it's not going to be the big rip, it's not going to be the big crunch, it's probably going to be the big freeze. But, which is kind of the most pleasant of those three options. There are a number of different studies going on and telescopes that have launched to try and constrain cosmological parameters. One is is PI'd out of this department here called SphereX, NASA SphereX, that launched a year and a half ago and has been in space observing many distant galaxies in ways that Katie was describing, looking at things like lensing and shear and all of these sorts of things. Euclid is another mission. There's a number of different missions that are taking more data to better precisely map the cosmological parameters and be able to better answer this question in a lot more detail. So we'll know more in the next few years as these missions do their objectives. Good question. Hard question starting it out here. Question in the back. Maybe not so hard, though.
This is for Professor Bouman. So I was just wondering, can you shed light on when you guys were stitching together all the data from, the different sites? Can you shed light on some of the biggest challenges in doing that, besides just the sheer volume of data?
Yeah, there's so many different challenges. The focus that I had was more on the challenges of the image reconstruction, which was actually not, the main challenge was not actually reconstructing an image, but it was actually verifying that that image was correct, or that we were making good conclusions from it, which was super scary, kept me up at night, that we would put something out and it would be totally wrong. But there were tons of different types of, across the whole project, lots of different challenges. For instance, when we collect the data, first getting just the instruments ready, being able to capture the light so well and everything. Then when we capture it, we actually were capturing petabytes of data, so much that you can't actually send that data over the internet. It would take like, we collect some data at the South Pole. I think sending the data from the South Pole via the internet would take something like 25 years. So there was challenges of even just sending the data. Then you actually have to do this process of calibration and correlation where you have specialized supercomputers that are actually there just crunch that data down. In the end, you go from petabytes of data to megabytes that you just like can email this file easily. Then there's also obviously the imaging challenges, and then there's the challenge of interpreting it. So I feel like there was challenges all along the way, not to mention even just the challenge of working with a couple hundred people across the globe and finding common times to meet, and all the political kind of personal challenges too of just dealing with that many people. But it was important because we brought together all these different types of people and different ideas, and I think that made our results stronger for that reason. I'll just highlight one of the challenges more on the imaging side again. When we first made the M87 data image, I didn't talk about it, but we actually, when we got the data, we didn't just sit there and make an image. What we did is we actually split ourselves into 4 different teams. And those 4 different teams, when we collected the data, we went into different rooms, or we just stopped. We did not communicate with anybody on the other teams. And we actually worked for about 7 weeks just in our teams on trying to make an image. And although amazingly, on the first day that we got the data, we pressed go and we actually got an image that looks actually amazingly similar to what we ended up publishing, we were still not sure if that was real. So we worked for 7 weeks on trying to verify if that was real, or we were just getting a ring out because we wanted to see a ring, even subconsciously. And then after 7 weeks, we all got together and we compared it. So there was more about not even just reconstructing the image, but validating that image was a bigger challenge.
Hi, Casey. I actually met you in 2019 at NeurIPS randomly at the Buds seminar, and I'm finishing up grad school. But I remember back then, sort of the big thing was, we had like deep learning, convolutional neural networks, and that sort of thing. So since then, there's been a lot of progress in machine learning. So how has the introduction of, say, diffusion models really impacted how you work with like noise in data and the sort of flexibility you have with models? And also, how can something like quantum computers embedding, where you could encode more states within, data, do you think that that's something that might be helpful in the future? Thank you.
Okay, well, I can comment on the diffusion models, and maybe I'll also pass it to Brandon, who works on these as well. So I didn't get into the details, but actually these image models, these AI models that we're training based upon these collections of images, the main backbone of what we've been using these days are diffusion models. So diffusion models, the idea is like super simple at its core. You have a collection of data. You basically noise that data. You add more and more noise until it just becomes static. And then basically we use an AI model to tell us how to denoise the image. And it learns how to take a really noisy image, make it a little less noisy, then a little less, and a little less. And so we basically learn a denoiser. And that allows us to generate images. And so if we start with a new a realization of noise, just random Gaussian noise, for instance, we just apply the same denoiser over and over again until we get back an image, and it will look like an image that from our training set. Now the challenge is plugging that information in with the physics of the measurements. And that's kind of what we've been working on, of developing methods that incorporate diffusion models, but also allow us to impose the physics of the measurements. I don't know, Brandon, if you have anything else to say.
I feel like you explained it pretty well. I think like one intuitive way to understand diffusion models maybe is like, I remember when I first heard about them, people were talking about like saying all these big words like diffusion and noising and annealing, and I was like, I have no idea what's actually going on. The way I understand it now, and the way I would explain it to someone, is kind of like what makes them special is like, I guess since you were born, let's say you saw many examples of a golden retriever, and so now in your head you've kind of like formulated some concept of what a golden retriever should look like. And if prompted, you could say whether or not something is a golden retriever or whether or not something is likely to be a golden retriever. But to do that, your brain has to store a very large amount of visual data, since sort of you're seeing things. And I think the main revolution in these machine learning models was more capacity issue. So like before in 2019, maybe we were messing around with models that have like, a certain amount of maybe like hundreds of thousands of parameters. But since then we've come up with, people like to package things and like put ribbons on them and make them sound fancy. But I think the main development since then, which has been really nice for our research especially, is that we've found ways to train these much larger models that can actually have enough storage capacity to not only form, I guess, concepts of what a golden retriever looks like, but actually like what would dark matter look like under certain physical assumptions and sort of like delineate between those things. Hopefully I didn't make you guys more confused instead of not as, but yeah.
So
An
dark
answer
matter,
for the quantum computing if someone else wants to take that, but I don't know any quantum.
dark matter is not a golden retriever. It's not composed of golden retrievers. Okay.
This is pretty similar to the last question, I guess, and it might be kind of getting into the weeds, but I was just kind of curious, because we're opening the door to like diffusion models, and typically like you can look at a picture of a golden retriever if you're generating a bunch of pictures of golden retrievers, and you can very much say, okay, this is what's right, this is wrong, this is what aligns with my priors. People use like classifier free guidance to kind of guide the distribution somewhere. I was kind of wondering, how do you, like, if besides the physical equations, is there some way you validate the outputs so that they're actually useful for your task, I guess?
Okay, so I don't know if this answers the question, but we actually have a paper that was recently put on arXiv and is in submission, which actually has black holes and golden retrievers in it, actually. I don't know if you chose that for that reason. It was another student. But actually it was on, we have some work that it's on, okay, like if we use some sort of diffusion model, for instance, to help us push our solution into a certain regime that looks like certain kind of images, maybe we're only getting images that look like these black hole simulations because we pushed it so hard, and that's not good either. So we have some work on, I didn't talk about it today, but we have work on evaluating what is the probability that we would see measurements if this was the true distribution of what the image came from. So you can, for instance, take the distribution of images of simulations and evaluate what's the probability that the measurements of the real black hole I see lay within that distribution. You can do that for other types of images, other types of models of black holes, different models, and see which one, how does it compare. You could also do it for we've also done it for crazy things like the faces example. And you actually find that, okay, yeah, like obviously we don't believe that the black hole looks like a face, but what's important is not exactly what it looks like. Again, it's about finding a prior that is flexible enough to be able to describe your data, but not so flexible that it doesn't allow you to say anything. And through that, we can try to evaluate what is a good prior that we actually trust the result of and is not biasing us too much. But then we can also test, does it look like the data is within this and within this distribution? And we find that for at least the M87 static imaging data, it seems like it's within the distribution of these complicated, detailed simulations of black holes, but it's not so in distribution that it's not, there's still room for improvement in the model. So through that, we're trying to think about, can we identify not just if it's in distribution or not, but can we modify our model? Should we modify our model to actually better fit the measurements, and can we learn any physics through that?
Thank you so much.
And we also do it, just to go back to the golden retriever, we have like an image that is blurry of a dog that is half corgi, half golden retriever, and it identifies it's not a poodle, but it is a half corgi, half golden retriever.
All right, so I know that black holes will often have the kind of jets separate from their accretion disks. Is it possible to, with the imaging that you have, be able to like image those jets? And is it also possible with the data that you have to confidently say what the orientation of the black hole is, relative to our line of sight?
Yeah, so for the M87 black hole, we know that there is a jet because we can see the jet at other wavelengths. And so we actually know that the jet is coming at us at about a 20-degree angle. And so if we expect the accretion disk that is causing the light that we see, that shadow that we expect is mostly causing that shadow, if we think it's perpendicular from that, that's how we get things like we know the direction of how the gas is spinning around the black hole and stuff. But we actually currently I would say don't really see the jet. I mean, there's some evidence that maybe you can see a little bit of the jet, but it's for the most part, we can't see the jet using the telescope separations and orientations that we have already for the Event Horizon Telescope. But it is a big, important problem to try to actually get that jet accretion disk jet connection and understand how those interact. And so actually one big priority is we've been adding telescopes to the telescope array, and actually been taking data more recently. And hopefully when we have actually telescopes that are closer together, not farther apart, actually, we can start to maybe see that jet accretion disk connection. So that's one interesting thing. For Sgr Star, we actually don't know if there's a jet. So doing things like that might help us in the future. And I don't know if others have other.
I could add something real quick about the small black holes in our galaxy and also the big ones. A lot of them actually do have a jet and do have an accretion disk, and we see it in multiple wavelengths. And a primary wavelength that we can see the jet is actually in the radio, because as you launch particles, they gyrate, which you might have seen, and their interactions with magnetic fields give off light at radio wavelengths. So when we point our huge radio dishes at these black holes in our own galaxy, some of which are only a few thousand light years away, we see not only this phenomena that was shown on 1/1,000,000th of the scale, you see this little tiny accretion disk and this little tiny jet compared to these, these monster systems that were shown from Katie, but they are ubiquitous, and it's because the physics is fundamentally the same.
I also wanted to add, like, if you want to see jets, there's like, I think in the grand scheme of, like, they've been imaging jets since like the 1980s, like, because jets are a lot bigger than black holes for the most part. If you want to, like, great thing to Google if you have time. There's like Cygnus A. So there's been a lot of jet radio programs, and in general, because they're quite a bit bigger than the actual event horizon, they're kind of, you don't have to do this driving trucks of petabyte hard drives thing around. You can just kind of like set up an array of telescopes and look at them. But yeah, they look very cool though. I would recommend Google image searching.
Notably, I'll just mention, we had a lecture that happened through this program last year by a postdoc named Martijn Ooi, who talked all about the discovery of the largest jets from galaxies in the universe, that are the jets from a galaxy that's on par with the Milky Way or the M87 system that Katie talked about earlier. Their jets extend better part of 3 million light years away from the supermassive black hole in the center. And you can see it in the radio in these beautiful, beautiful images. So look up on our YouTube if you want to learn more. It's a really good presentation.
Thank you. So in your presentation, I saw a slide showing that the light behind the black hole like bend because of the gravity, and so that's give you the ring. So my question is, when you take a picture of the black hole, is it you are waiting for some bright star behind the black hole to give you the ring, or because of the photon like circling around the black hole always give you the ring? So which way? That's first question. Second question is, I saw all the picture in publication. The black hole picture is like orange, yellow color. Is it a real color or is it a artificial color? Or different black holes should have a different color?
Yeah, I'll answer that one first, I guess. No, we don't. It's just a fake pseudo color. We are observing in non-visible wavelengths, so it's about a 1 millimeter wavelength. It's a short radio wavelength, so we as humans don't see that color, but it's also essentially one wavelength of light, so it's monochromatic or whatever. But it was actually a big thing going back to like the, working with a big collaboration. We even had a few of us that actually studied, well, what color map should we use for this? And we actually created different color maps, and we decided on that one because it was perceptually uniform, but also gave a sense of the heat because it's really hot around there. So that's why, but it's better than the black and white in allowing you to actually see the different structures. As for your first question, also really good question. We expect around the black hole that we have this accretion disk, this gas that's orbiting around it. And no, we don't. So we expect that there's always kind of like stuff going around the black hole. And actually from any orientation that we see the black hole, we expect that the light bends around it. So you're always going to get a ring of light that's related to that photon orbit that I talked about. But actually, depending on the orientation that you observe the black hole, if you're edge on, it's going to become more of a crescent shape because there's more actually something called Doppler boosting that's happening, where the light, when it's coming at you much faster in one direction than the other, and that causes the light to be brighter on one side than the other side. Whereas if you're closer to face on, there's less of a difference in the velocity, the velocity towards us of the gas, and so you don't get as much of a crescent shape and more of a ring shape. So you're always going to see a ring. It's just the amount of brightness asymmetry actually changes. I don't know if others want to.
There was a question. Thank you. Quick question about dark matter. Can you tell us a little bit about the presence of dark matter? If we have any information about the presence, are they distributed everywhere, or they're limited to certain areas we know, or are they in our solar system or farther? Or can you just talk a little bit about that?
Yeah, it's a really good question. I think a lot of the precise answers to some of those questions are yet to be sort of concretely decided. The main reason we suspect that dark matter exists, or that it exists, and there's a lot of evidence for it, I don't want to undersell it, is that kind of related to what Katie mentioned in her talk. A lot of times when you look at things that are very far away and might be sitting behind something, you expect, depending on how massive the object is, that the image will be distorted in a certain way, or maybe it will be offset by a little bit. This was, I think, famously observed when people were looking at stuff behind the sun a while ago, but this is kind of all evidence of Einstein's theory of general relativity. The thing is that for most of the sky, when you look at very large objects like galaxy clusters, you expect we kind of know the mass of the visible stuff that's in the galaxy cluster just by sort of measuring it. And when you observe stuff behind the galaxy cluster, it ends up bending a lot more than you would expect than the mass from the galaxy cluster could explain. And that repeatedly observed over very large portions of the sky is, I think, one of the biggest pieces of evidence for dark matter. As to where it is, that is a question we hope to answer. Doing dark matter mapping and yeah.
I'll add a little to that. So another piece of information that points towards the presence of dark matter is indeed the lensing effect, the warping of the light around those massive structures that suggests there's more mass there, but also the presence of mass causes things to, when they're orbiting around it, to move faster than they otherwise would. So for instance, when you observe a galaxy, you can, as Brandon mentioned, you can kind of look at all the light that's coming from it in terms of the normal matter that's luminous, whether that's gas, whether that's stars, and you can effectively estimate how much its mass should be from the normal matter, from this luminous matter, from the light that it puts out. But then you can also measure the speed at which things are orbiting around it, stars or clusters of stars or something like that. And they're moving much faster than you would otherwise think they would if you assumed the luminous matter was the entire mass that was there. And they're moving so quickly, in fact, that they would spin themselves apart. They wouldn't be able to hold themselves together in the same way that the example I always use is if you get on a merry-go-round or a carousel and it starts moving. If it goes too quickly, you need to hang on to something or you're going to go flying off. It's the same thing, but instead of hanging physically onto something, the force that holds it together is gravity. And so there has to be enough mass there to have enough gravitational force to hold it together at the speed at which it's traveling. And that mass, if you just assumed it was the luminous matter, it wouldn't be enough and things would fly apart. So that's another way that we know that dark matter is present. It tends to be clustered on scales of galaxies or clusters of galaxies. It doesn't tend to be clustered on smaller scales. So our solar system may have dark matter passing through it, but there's not a big clump of dark matter sitting on our solar system. It's too low mass for dark matter seemingly to cluster on those scales. It's too dynamically hot to cluster on these small scales. So yeah, that was just a little bit more, but there are a lot of mysteries like what the dark matter physical structure is that we don't really understand, and is why there's so much focus in terms of research, both in terms of what we heard about tonight, but also theoretical modeling and observations at other wavelengths of light to try and determine what's going on with dark matter and where it is. Yeah.
I was wondering, I saw 2 images of black holes so far. So are you starting to see uniqueness between them, differences between them, or do they look and behave pretty much the same other than like maybe the jet is in a different direction or a certain distance away? They're different sizes, things like that. But do they have unique features, speed? Well, I guess the speeds could be different, but yeah. It's like the more we look, the more we see uniqueness in the universe.
Yeah, at a first order, remarkably, these 2 black holes are very different sizes. One is in the billions of sizes and one is in the millions of sizes. And despite that, and then you also talked about much even smaller black holes, but they actually all seem to be obeying what is predicted from general relativity. So at their first order, they're very similar, which itself is kind of amazing. But there are differences among them. So as I said, M87 is much, much bigger. It's the size of its event horizon is like larger than the size of Pluto's orbit around our sun. But the size of Sagittarius A star, the one in our own Milky Way, is much smaller, only a little less than the size of the Mercury's orbit around our sun. So very different sizes, but in both of them you have gas that's moving around close to the speed of light. But that means that the gas is, even if it's moving at the same speed, it makes a full orbit in a much different amount of time. So whereas it takes like 4 to 30 days for the gas to make a full orbit around M87, it can complete a full orbit in like 4 to 30 minutes for Sagittarius A star. And so that's part of the reason it took us 3 more years to image Sagittarius A star, because in the time that we're actually observing the black hole over the course of a night as the Earth is rotating, it's actually changing from minute to minute. And so we can't, it's like trying to take a picture of a moving object, something moving. So yeah, that is something that is very different between them, and we're trying to make movies of both of them. Actually, we just are completing a observation run for M87, where we actually were able to get observing time imaging at multiple times a week over a period of a number of weeks. So hopefully we can make a movie of M87, and then also been working on making movies of Sagittarius A star from just even a single night of data.
One thing I'll just add really quickly to that. Black holes intrinsically are very simple structures. I think John Wheeler famously said black holes have no hair, implying that they basically, you can describe a person by you know, their height and their weight, and if they have a beard, and if they have short hair or long hair, you know, 1,000 different characteristics. We're all unique, right? But black holes basically have 3 different properties, or 3 different quantities associated with it. They have a mass, which also dictates their size. They have a spin, how quickly they're rotating, and then they have a charge, an electric charge. How many electrons or protons that are associated with that particular thing, which for most macroscopic black holes is basically the charge is 0. Because if you have a positive charge, you're going to more effectively attract negative stuff to you, and it's going to negate. So for the most part, black holes really only have 2 properties. And so it's not perhaps a surprise that these images may, even though, I mean, these are different by a factor of 1,000, M87 and Sagittarius A star, which is different by a factor of 1,000,000 relative to a stellar mass black hole. But that's one of the properties that can change, and the other is basically the rotation rate. And then maybe the environment, like one might have an accretion disk at this moment, whereas another doesn't. But they're really intrinsically very simple objects, even though, you know, they have a lot of complexity potentially in the mass distribution that went into them over their history, but that doesn't really matter for their property right now. Yes, please.
So, and if you're interested in like what kinds of different masses do we see for black holes and what kinds of different spins do we see, this is an active area of research in my field, where now that we've been observing gravitational waves for the last 10 years and we have something like 300 events, we can start to do studies of the population of black holes and say something about, well, how many are around 10 solar masses? How many are around 30 solar masses? Are there more massive ones? How do those form? And you can start to make inferences about the formation channels of these black holes and the black holes that go into these mergers. Like how fast are they spinning and that kind of stuff.
Yeah, the gravitational wave stuff, I feel like has really opened up a whole new view on black holes in general. So.
That is the phrase that everyone has been saying for the last 10 years, a
Right.
new era,
New era,
of
indeed.
gravitational wave astronomy, a new window into the universe, because gravitational waves give us a completely new way to observe these objects. It's separate from the electromagnetic spectrum.
Yeah, that's great.
Actually, I have to
Oh, yes.
head off. This has been amazing. I'm happy to talk, have more questions at any other time, but thank you so much for everything. I also really think that we should, Kristen deserves a huge applause for being an amazing mom here. So thank you very much, and I appreciate it.
We'll continue our panel, but sadly without Katie.
Can I ask a question really quick before she leaves? Between Sag A and M87, the observations, on Sag A, we see 3 lobes. On M87, we only see 1 lobe. Are those artifacts, or are they really reflective of something that's happened?
Yeah, great question. I didn't get into it in the talk. For M87, we believe it's really like that, and that it's related to probably something not fully, but to the direction of the gas is spinning. For Sagittarius A star, it's due to our uncertainty, largely because Sag A star is evolving quickly and it's hard to pin it down. And we see when we have, and actually we get different images with the lobes kind of in different places. So that's due to the averaging effect of lots of images. So don't trust that. Yeah.
Thank you.
Additional questions? Yeah.
A question not related to black holes. In a binary triple star, do they all have planets revolving around the stars? And then like how do they behave planets being closer to other stars? And then like could they collide with each other, planets or whatever?
Yeah, that's a fantastic question. And I'll start, as everyone says, it's an active area of research, but we have a lot of progress. So if we look at our closest star to us, the closest star to us, Alpha Centauri, it's a triple star system. And that already tells you how common triple star systems are. And we have really good reason to believe that around at least 1 or 2 of the stars in that triple star system, there are planets. And we observe at least 1. And so planets can survive in those environments. And that's so interesting that they made a Netflix show about it called The 3-Body Problem, where you have a triple star system and a planet. And so they are at least ubiquitous in our closest neighbor. Now, the question is, what's the fate of planets that are in these unstable or chaotic triple star systems? And the answer is it really depends on the configuration. How close are the 3 stars? What are their relative inclinations to one another? And one thing that we know for sure can happen is you are a planet and you're undergoing chaotic physics where your orbit is changing because of the other stars exerting a gravitational influence on you. Thankfully, we don't have another star to do that. But as a result, you get plunged into your host star. So imagine if there's another star tugging on Earth and making us go into such a radical orbit that we plunged into the sun. Thankfully, we don't have to worry about that, but there are other planets that have to. And sometimes we look at stars and the elements in these stars, and we're like, that should not be in a star, that should be in a planet. And we infer that that star at some point ate another planet. Secondarily, we observe planets that are so close to their stars, much closer than Mercury is to our sun, that they could have only got there by just missing the host star as they were about to plunge in. And these are called hot Jupiters because they're Jupiter-sized planets that are right grazing their host stars. So this definitely happens, and both stellar companions and other planetary companions can have aggressive effects on the evolution of a planet. So that's a really good question.
Before I take another question from our in-person audience, I wanted to point out, if people haven't had a chance to look through the telescopes and they want to look through the telescopes, they're going to shut them down in about 5 minutes. So yeah, anyways. So if you want to check it out, now's the time, but no pressure. You can stick around for our Q&A as well. There was a question from our online audience that there were a few, but the first one I wanted to ask was, someone asked, what's the end stage of galaxies? When galaxies end their life, is it like we talked about the first question we had, a big crunch where everything collapses down onto the supermassive black hole, or something else? And the response is, in general, galaxies don't really have an end point. Galaxies, for the most part, are growing. They accrete, they merge together into larger and larger structures, or if they are far enough away from companions, they'll just keep doing their thing. They'll eventually use up their gas to form new stars, and they'll turn into something like an elliptical galaxy, like M87 is a good example of that. A massive galaxy that's composed of just stars, but doesn't have a lot of active new generations of stars being created. But there isn't really a dissipation mechanism for dispersing a galaxy, unless, I guess, you could have a close passage with another object that kind of tears up one of the objects, but eventually that'll probably fall back onto the other object. So for the most part, galaxies just grow. It's termed hierarchically. They merge together, they form a more massive one, and then that merges with another one and forms a more massive one. So it's kind of a one-way direction as opposed to a dispersal thing. So in some ways, galaxies are kind of immortal, which is pretty cool to think about. But anyway, that was the question from online. We'll take more questions from in person.
Thank you. So have you guys heard of the bitter lesson with the machine learning, like the machine learning field? No? The bitter lesson?
I as the machine learning guy, I guess. Yeah.
Huh?
Yes. Yes.
Yes. Okay. So in your case, in your guys' method, you guys mentioned bias in like a previous question and within the lecture. What other forms of bias have you guys found within your method? And as is in the perspective of the bitter lesson, scale typically out or through a long enough horizon will outscale and outperform methods that rely on embedding expert knowledge within data or architecture or computational methods. So what ways of scaling and what ways of, what kind of bias have you found within your method?
So I'll answer the scaling question first. For those in the audience who aren't familiar, the bitter lesson is sort of this famous essay in machine learning where, so when you design a machine learning model to do something, there's often a big temptation as sort of a designer to make the model try and think the way that a human would think about a problem. And the bitter lesson was, in the context of a lot of like the sort of AI slop that you see today, like where for example, you want an AI to make you a picture of a golden retriever, or you want it to tell you if it's looking at a picture of hot dogs or legs. It's often much more effective to train it on a very large amount of data that is just labeled and suited to your task than it is to spend a lot of time trying to make it, for example, obey the laws of physics. In the context of astrophysics, I would say that honestly, at the stage we are in right now, we don't have billions of labeled examples, paired examples of observations of, for example, black holes and what the actual black hole looks like. We don't even have one ground truth image of what the black hole looks like. We still have reconstructions. To that end, I would say that, I mean, I hope we get better lessened, right? I hope that one day we have, you know, so many pictures of black holes and their corresponding measurements, and so many like images of dark matter and their corresponding measurements that, I mean, we can all, you know, pack it up and go home. Unfortunately, unlike pictures of golden retrievers, there isn't this like huge data repository that we can take advantage of to sort of scale with the bitter lesson, which is why we have to resort to what machine learning people sort of arrogantly call bias, which is just saying like, oh, well, we know how physics works. Let's use that to constrain our reconstruction rather than trying to train it with blind paired examples. In terms of bias, it's a really big question. Like, I mean, depending on how you interpret it, it could just be like, how do you know what you're doing isn't wrong? I think it's kind of a philosophical question with science and otherwise. I think in our context, our being Katie and I, because I don't want to speak for the real astrophysicists here, but the general strategy for validating your method in the context when you don't have a ground truth. By ground truth, I just mean, let's say I went out and I took a picture of a black hole. How do I know it's the real picture of the black hole? Because I don't know what the black hole actually looks like. The way that you typically go about validating these things is you come up with every single thing that you think a black hole image physically should obey, every single law of physics. In the dark matter case, this actually is kind of more of a statistical question. What do we know statistically about the matter distribution on large scales from what a lot of people smarter than me developed in the field of cosmology to validate that what you reconstructed actually is sort of like plausible and can like fit within some physically plausible explanation. Turns out if you sit down and make a list of things that your reconstruction should obey, you can come up with a lot of them. And kind of the best thing you can do is just make sure that every single thing that you think should be true about your reconstruction, that you know should be true about your reconstruction, actually is true.
Sounds like a challenging problem.
Not for imaging black holes, but for a bunch of other areas in astronomy and physics, there are cases where we need help training the machines. And so we actually need people, like real humans, to look at these images. And because real humans are really good at learning from a couple of examples, and then they can classify these images and help train the machine. So projects like the Zooniverse project allow citizen scientists to go online, and you can, within a couple of clicks, learn how to do this yourself and help train the machines to do this kind of research. This is a thing in gravitational wave science where we're trying to classify glitches in the detector, for instance. And pigeons. Oh.
Yeah, the Zooniverse is a great website that people can visit to do citizen science and contribute towards real scientific endeavors and be part of real scientific papers as well. I'm going to go with a few more people. You haven't asked a question.
Yeah, I wanted to know why dark matter around galaxies, clumps, presents itself as a halo as opposed to like a rotating disk that the visible matter presents. And also, are there subclumps of dark matter in the halo of dark matter? And exactly why wouldn't it, over the course of billions of years, come to establish a rotating disk?
These are good questions. I can take this if that's okay. Okay. So the questions about dark matter. So I think during Katie's talk, she showed an image of a cosmological simulation, right? Early on, that was showing kind of a bunch of bright structures that look kind of spherical in shape, kind of clustered together, and kind of, people refer to this as the cosmic web, because it's the underlying structure of how matter is distributed on very large scales. And it has a kind of a web-like, a three-dimensional web-like shape. But the first of your questions is, why does it look spherical? Why does a dark matter clump in spherical distribution as opposed to any kind of rotation-based thing or disky like we see with the spiral disk galaxy or something like that? For the most part, we think that the dark matter doesn't have a way of dissipating energy where it can shed energy but not angular momentum in the same way that normal matter does. So one way in which normal baryonic material, protons, electrons, and the like, can shed energy without shedding angular momentum, which turns into these kind of disk-like structures, is through radiation, through light, through electromagnetic radiation. And we don't think, it's possible, but we don't think that dark matter has the capability of expelling energy in that same capacity, that it continues to hold this energy, and so it can't shed that energy while keeping angular momentum fixed, which is what allows these rotation-based structures to occur. However, it may be possible for there to be rotation associated with dark matter, and we see that galaxies may have spin and rotation to them in their dark matter component, but not at the same level as the normal material does, not down into these thin disks. But ultimately, we haven't been able to image, Brennan and Katie both were talking about the ways in which we're imaging the dark matter or the black hole or anything is predicated on some of the physical models and what we expect for it. So it allows us to better constrain things if you abide by our preconceived notions of what it's supposed to do based on the laws of physics. But if you back out and don't have any priors, then you have a more general solution, and maybe you can't get as much information out of that as well. So it's a trade-off. But thus far, we don't see a lot of dark matter halos from the simulations that suggest that there's a strong amount of rotation in these structures.
Yeah. I think you also asked if there's subclumps, and yes, the answer is yes. For bigger things like galaxy clusters, a lot of like Cameron mentioned earlier, a lot of the evidence for dark matter is that things are rotating faster than we expect them to be. And I hope I don't butcher this, but if you look at a lot of things that are rotating around, for say a galaxy cluster, you can measure how fast they're rotating as a function of how far they are away from the center. And you'd expect if something was perfectly spherically symmetric, then you'd get a certain decay of, like, if something's further out, then it rotates at a certain velocity, but you realize that there's sort of like a non-monotonically sort of decaying velocity profile. So basically what I'm trying to say is that there's a lot of evidence for there being subclumps in these larger clumps. And if you zoom out even more past the scale of galaxy clusters to what we call the large scale structure, you get something that doesn't really anymore look like just, like raindrops or just like a bunch of dots. What you get is kind of this cosmic web of interconnected dots. So that you have these like big empty areas, and then you have these huge peaks, and the peaks are kind of like loosely connected with like filaments and stuff like that.
Yeah, subhalos, dark matter subhalos are thought to exist, and one of the active fields of research today is looking for their effects on cold dynamical structures like stellar streams that are formed by tearing apart star clusters as they enter our galaxy, or other galaxies as they enter, because the presence of these dark matter subhalos and subclumps will effectively disperse those cold kinematic structures with a particular signature. So this is, we'll hear more about it in 2 weeks at the Astronomy on Taps. There'll be more talk about dark matter there. So additional questions? Yeah. That's okay.
Gosh, I have several. Just one? It has to be a good one then. Okay. Shoot. All right. Okay, there we go. There we go. That's it's like, okay, like graduate seminar. Okay. Am I correct in understanding from what Katie said that there are only these two candidates for observation of galactic black holes right now? And is that, do we have any other possibilities is my question.
I think there are other candidates, but those are the ones, both M87 and Sagittarius A star are the largest, have the largest angular size, because Sagittarius A star is the closest supermassive black hole to us because it's in our own galaxy. And M87 happens to be a similar angular size, like the difference between the size you are in my vision and the size of my thumb is, they're about the same right now. Of course, my thumb intrinsically is 100 times smaller than you, but it's 100 times closer to my eye than you. And so these are the two kind of scales of the Sagittarius A star and M87. And all the other supermassive black holes that are out there exist, and we can try this. It's just harder to do because they have a smaller angular size relative to us, because they're either farther away or they're intrinsically smaller.
And our telescope is only the size of the
It's
diameter
only
of
the
Earth.
size of the Earth. So,
Yeah.
you know, yeah. Yes. So there are efforts to, as Katie alluded to have larger baselines between your between your different telescopes to allow you to get finer scales. But we might as well get finer scales on the two supermassive black holes that are already the largest that we can see. But yeah, they'll start doing it for. Do you want to add to this, Brian?
Yeah, just like fun fact, the Soviet Union used to have a radio telescope in space.
Oh, did it?
Yeah, but it's decommissioned now. I think it was called Astron or something. Or yeah. I didn't just spread misinformation.
Misinformation.
I'm like
Fake
reasonably
news
sure
here.
that I'm not crazy.
Any other people who haven't asked a question yet who have a question?
Thanks. Question about the intergalactic medium. From what I understand, it was ionized when the universe first began. Then it became deionized. Now it's been reionized. Is there a general consensus as to when it's going to continue to be ionized ad infinitum, or is it going to be re-deionized at some point? I mean, I'm sure it depends on your cosmological model, but I mean, what are the thoughts there?
I can talk about it, but I've talked about everything. So I work on it too. So, so just to make sure everybody's clear on the question. So there's stuff in space. Okay, there's stuff in space. That stuff tends to be more clustered around galaxies because there's more dark matter, there's more mass that pulls, has gravity that pulls things into that galaxy. So the densest stuff in space in the plane of galaxies like our own Milky Way is called the ISM, the interstellar medium. And when I say densest, this is like still, when we make a vacuum here on Earth, not like a vacuum machine, but like a vacuum chamber, that level of density is on par with the density of this stuff that's in space. And that's the densest stuff in space. So that's called the ISM, the interstellar medium. Then there's something called the intergalactic medium, which is the stuff that's in between galaxies themselves. It's much, much lower density. It's like probably 1 million or 1 billion times lower density. We're talking like a single particle in a cubic meter of volume, like a single atom in a cubic meter of volume. Very, very low density. And the question was about that stuff, that intergalactic medium, that stuff in between galaxies. And initially in the early universe, well, initially right after the Big Bang, it was all ionized. Being ionized means that you've basically knocked the electrons off of the atom, so it's just a soup of electrons and protons, if you're dealing with hydrogen and helium alone. And so that was true because in the early universe, it was dense and it was very, very hot. And so everything was ionized. Then the universe expanded. And so things cooled off and those electrons were able to join with their protons and form hydrogen, neutral hydrogen atoms. And so there was a period of the neutral universe that we refer to as the dark ages, because there weren't yet the formation of stars, the formation of galaxies, and so on and so forth. This is anywhere from just after, let's see, what was the 300,000 years after the Big Bang to about 80 million years after the Big Bang is considered the dark ages. Then the first stars formed and the first galaxies, and they were pumping out so much radiation and light that it, again, ionized that stuff. It kicked off the electrons through these energetic photons. And now most of the intergalactic medium is ionized. It's just being irradiated by all the starlight and all the light from supermassive black holes and the accretion disks and the jets from them. In the distant future, if we believe cosmological models, which I think there's reason to believe, galaxies will get farther and farther apart, and there will be more space in between them. Similarly, galaxies will eventually run out of gas and fuel to form new generations of stars. So there will be less radiation throughout the universe, and the space between galaxies will be much, much larger. The volume around galaxies will be much, much larger. And so again, I don't think that this is a crazy prediction. I just thought about this. I presume that in the distant future, it will again go back to neutral. The IGM should be, the intergalactic medium should be neutral again and not ionized in the distant future. But I can't tell you exactly what time scale that would be. Presumably another Hubble timescale, the age of the universe, or longer into the future. But yes, I think it will go back to being neutral at some point in the distant future. And stay like that. Yeah. Oh, and that's our last. Oh, no.
It's just at 10 o'clock. It's just you don't get any more microphones.
What the heck? That's okay. Sorry about that. I guess there was a hard cutoff at 10 o'clock. That's never happened before. Thank you guys for sticking around. Let's thank our speakers, our panelists. We thank Katie in absence. And as I mentioned at the beginning, we do these once a month. Our next one of these will be Friday, June 26th, the final Friday in June. And I don't yet know who our speaker will be. Similarly, we have Astronomy on Tap that happens at a bar in Old Town Pasadena, the Doghouse Beer Garden. We will have 3 of those in 2.5 weeks' time, Monday, Tuesday, Wednesday, June 15th, 16th, and 17th, and be speakers from all around the country here for the American Astronomical Society. And there will be the Astro Fest festival taking place at the Pasadena Convention Center on Sunday, June 14th from 1 to 5 p.m. Lots of science demos, 30-minute public level science presentations from scientists from around the world, all free and open to everyone. So I'll put up the announcements for all of that stuff in the next few days on our website and on social media and all the places. So thank you guys for coming. We'll see you guys next month.